It is a pleasure to introduce the third speaker this morning at Irrational Fans in Physics and Mathematics, Miami, Florida, Institute for Mathematical Sciences of the Americas. And one of the objectives of IMSA is to create this dialogue between North and South, especially with Latin America, Miami being a natural center of activity for Latin American mathematics. And it's a great pleasure to have the first Latin American speaker today. One of the pioneers, just as Professor Prato, in the field, Professor Alberto Verjovsky. And he was thinking about these objects even in the 80s, I believe. Well, he'll tell us the story probably. In any case, it's a pleasure to have Professor Alberto Verjovsky speaking about, from UNAM, Instituto de Matemáticas, UNAM, talking about the intersection of quadrics in ZN, complex manifolds, and convex polytopes. Alberto?
Well, thank you very much for the invitation. It's a pleasure and an honor to be here. I thank the organizers, especially Ernesto. So the title, it's already there. I would like to start by telling that this was created at the end of the 80s. It's in collaboration with Santiago Lopez de Medrano. And we both come from the field of dynamical systems. And as a consequence, words like toric, algebraic geometry, F-vector, Delzam polytopes, we didn't consider it. We just were working on dynamical systems. And we realized that we could, using dynamical systems, and in fact, the simplest one, linear dynamical systems in the complex domain, we could obtain infinitely many new examples of manifolds, which were complex manifolds, compact, but we were not symplectic. The second homology group was 0, and therefore they couldn't be algebraic. They were not, they generalized, in fact, as you will see, the classical examples of Hopf and Calabi-Ekman, which were the first examples of non-Kähler complex manifolds. So let me start. So you take two integers, m and n, two positive natural numbers, so that n is greater than 2m. So here m will be the number of linear equations, and n will be the linear space in which these linear vector fields act. So we take an n-tuple of vectors in Cm, where each vector is expressed as this m-tuple. And this configuration of vectors in Cm, of course, once you have these vectors in these m vectors, well, you can take the complex whole, but let's do it a little. So once you have this, you consider these linear systems given by the equation star. So you take these vector fields acting in Cn, are n variables, and j varies from 1 to n. So we have m linear fields in Cm, which are diagonal. In fact, it's simpler to express them with matrix as this. So is this a differential equation as we see in a course at the first years of university. This is a diagonal matrix. And here I use always the psychological trick of using capital T reserved for complex and a lowercase t for real, where Z is a column vector. So it's a standard linear system in the complex domain. So we have n differential equations. These are diagonal matrix, so they commute. And so I have n commutative vector fields in Cn. And therefore, if they will give rise to an action of Cm in Cn. And in general, these vector fields will be linearly independent, dependent, etc. So if we integrate the equations, we will get something interesting. But before that, let me tell you how this led to a construction of an infinite family of non-symplectic compact complex manifolds. So you take the same conditions, and then this configuration, you take the convex hull of these n vectors. These vectors are each of dimension m, and you take the convex hull of those, and you have the following two conditions. The Siegel condition, 0 belongs to the convex hull, denoted by calligraphic H. And the second is the weak hyperbolicity condition. This for every 2m tuple of integers satisfying this condition, we have the 0 is not a convex hull. So this is too many words, but what it really means is the following. Can be formulated geometrically in the following way. The convex polytope contains 0, but neither external nor internal facets. So you have, of course, the boundary facets, but you also have the internal facet. 0 doesn't belong to any of them, okay? And if you have that in these vectors, you see you have lambda and you add a 1. Therefore, you have a matrix, m plus 1 times n. And this condition simply means that this matrix, this rectangular matrix, has maximal rank. And well, this is the condition, you see. These are is one differential equation, m equal to 1, acting in C4. So you have this, the convex hull of this is this quadrilateral, and 0 is in the interior, is in the convex hull, but does not belong to any diagonal. That's what it means. In general, you have a polytope that of bigger dimension, you have that. So one consider what will integrate the vector fields, and we consider the holomorphic singular foliation. Here, singular means that the dimension of the orbits is different. You don't have a locally free action. A little later, you will see there's an open set with the action is locally free. But for instance, the coordinate axes are solutions of the differential equation, and the orbits are of dimension 1. So you have orbits of different dimension. The maximum dimension will be m. And here we know how to integrate these things by using exponential function. We know that linear equations are obtained by exponentiating the matrix. And so we have this action of Cm, but actually you see, because it's a linear action, it permutes the complex lines to the origin in Cn, and therefore we can projectivize the action, and we have this action in Pn minus 1. Here, these brackets refer to projective coordinates, and this is, you have this, and here is the exponential of lambda I, lambda 1t, lambda 2t, where t is a vector in Cm, z is a projective coordinate, and this here means the inner product. You don't use bars. So it's lambda 1t1, lambda 2t1, etc. as products. And then you have this action, and you have therefore a foliation of Cn. And so the solidified foliation is degenerate. It's exactly what I say, has leads to different dimensions. In particular, for instance, there's one, the smallest orbit is 0, because I'm assuming that all the matrices in fact are non-singular. I forget to say that. In particular, 0 is a singular point and it's the only singularity. And the behavior in a neighborhood of 0 determines two different sorts of leaves. So here you see the following definition. You have L, a leaf of the previous foliation. So you have a dichotomy. If 0 belongs to the closure of L, we say that L is a Poincaré leaf. And here you can see that this comes directly from dynamical systems, from the work of Poincaré, in fact, from the thesis of Henri Poincaré, and is called a Siegel leaf if the opposite happens. Siegel also was working on celestial mechanics, so this is completely dynamical systems, as I say. We're unaware of geometric invariant theory, toric varieties, etc. We just were working in the realm of dynamical systems. So the dichotomy is 0 is in the if 0 belongs to the if 0 does not belong, is outside of the convex hull, then every leaf is Poincaré type. Every leaf approaches 0. And the set of Siegel leaves is not empty if and only if 0 actually belongs to the convex hull. So here you have a schematic picture, very interesting. So here you have, this of course is schematic, is supposed to be Cn. The leaves are quotients of Cm. And here you have a single leaf, does not approach zero. Here you have Poincaré leaves that approach zero. And it's very interesting because it's very closely related to geometric invariant theory and the Kempf-Ness criterion. Okay, so you have this dichotomy, you have leaves. If zero is in the convex hull, you have, in fact, an open set of single leaves, as you will see in a few moments. And this is the Poincaré case. Every leaf is Poincaré here. Namely, zero is not contained in the convex hull. Every leaf approaches zero. And well, you define S the following for each Z for each Z in Cn. You have a number of indexes where the coordinates do not vanish, and you define S as these sets. Forget about what it is. It's just the complement. S is the complement of subspaces contained in the coordinate hyperplanes. So it's an algebraic set, union of subspaces of different dimensions. Therefore, the complement is open. And the complement is fantastic because the complement consists all of single leaves. All leaves there do not accumulate to zero. And then one beautiful thing about this linear system is the fact that if a leaf does not approach zero, it contains a one and only one point, which is closest to the origin. And now you see the connection between Hilbert criterion, Mumford criterion of geometric invariant theory. But of course, Santiago and myself were not aware of that. And we simply observed that if a leaf is a single leaf, it contains a point which is closest to the origin. And if you take therefore the tangent space to the orbit and the vector, they have to be orthogonal if they want to minimize the distance. It's just a simple elementary calculus fact. And that means that the set of points satisfying this condition is exactly the set of points which are at minimal distance to the origin. Sorry. And so today the set tau or t, cursive t, the set of all points in Cn different from zero that satisfies this equation. We observe that this equation, these lambda are vectors, so it's a vector equation. And already here we see something, and then we can projectivize this equation. You see this equation is homogeneous. If the vector z here multiplied by a complex number lambda different from zero, it still satisfies the equation. And so therefore you can projectivize this equation. And so you define n as the set of all points with projective coordinates z1, cn in Pn minus 1 that satisfies this homogeneous equation. So it's an intersection of real quadrics containing Pn. And here, let me stop to tell you something. You see, this equation is fantastic because you see it's invariant on the conjugation. If you take the vector z and take its conjugate, satisfies this equation. I mentioned this because this will be in a natural, very geometric, because that's what I want to emphasize, how geometric and how natural, how simple is this construction. Well, since it's invariant on the conjugation, this gives you a machine also to, as you will see later, to obtain real toric matches. I think Professor Frank Sotile has done some work on real toric manifolds. So this also gives you that. On the other hand, this equation, if you multiply the entries of z by unit complex numbers, well, it's also invariant. So it has a natural action of Cn. So it's very simple. And actually, if you think about it, you might think that intersection of quadrics is very reduced, is a very small set of manifolds. And actually, there's a theorem of Mumford, and there's a theorem that any manifold is the transverse intersection of quadrics. So this covers a lot of things. Okay, so you have this. And well, we can see the set S defined before is the union of this is what I told you. The set of Siegel leaves is an Zariski open set of Cn. In fact, it's just S, it's just Cn minus an analytic set with different components vanish, okay? And here is exactly what I told you. This equation expresses that the Siegel leaves have a point that minimizes its distance to the origin. And so that's what this equation. And this is very important because the weak hyperbolistic condition implies that this system of quadrics have maximum RAM. And so this set of points that define this equation by the implicit function theorem is actually a manifold of and this manifold tau for transversal, because this manifold, it will be a deleted cone which meets every single leaf in every single Siegel leaf in one point, and so in fact that means that the manifold tau is exactly can be identified with the leaf space because it meets each leaf in exactly one point. Therefore, this is one beautiful case where the orbit space is a manifold and reminiscent to the condition, to the stability, Mumford-Hilbert stability condition of geometric invariant theory. As I told you at that moment, we didn't know that, which were very dynamical systems. And everything, so I can reduce everything to the following fact. So if the Siegel condition and the weak hyperbolicity conditions are satisfied, then there is a manifold with actually a complex cone which is transverse to the leaves and meets every leaf at exactly one point, and therefore this quotient represents the leaf space. And now there's a beautiful theorem due to André Hefliger. Well, before going down, let me see. This is simply, I'm saying the fact that because M is a complex cone, namely, if one point is there, all complex multiples, non-zero complex multiples are also there. There's a natural projection of M into that, and therefore we have a principal C-star vibration. So what we do, because you say, well, there's a theorem of Hefliger that tells you if a manifold is transverse to a holomorphic foliation, and they have complementary dimensions, then actually this manifold is a complex manifold. So it's a beautiful way to obtain complex manifolds. You're lucky enough to obtain a manifold which is transverse to a holomorphic foliation. And that was the starting point of our work. But of course, the objection would be, yes, but it's not compact. But fortunately, this projection, you can compactify it, and this you projectivize it, and therefore this manifold M here is this manifold N is a complex manifold. But before going to that, every time you have a complex cone in Cn, one way to study is simply analyzing its intersection with the unit sphere S2n minus 1. So this is exactly what is here. We call M1 the intersection of points satisfying this set of quadratic equations with the unit sphere. And therefore, each complex line that belongs to M intersects the sphere into a circle. And therefore, you have a circle vibration, which really interesting there. And forget about that. I already told you that. The Siegel space has the same homotopy type as M, and that is because you can use the leaves to retract to M, and well, the M is the deleted cone, and so you can retract it to the unit sphere. Well, now let me point out something very interesting. Let me go back to the first page, almost the first page. Okay, so you integrate the question and you have this family of leaves. Think only of the leaves that do not accumulate to zero, the single leaves. The single leaves, and this is the manifold transversal, you see, forget about zero, it's a deleted cone. And this, of course, is disconnected, and this is just a schematic picture. But something I want you to see, if you take the action of C star to the N, obtained by the natural action of Cn, of C star to the N of multiplication of each coordinate with non-zero complex numbers, this action commutes with the linear action we define. And so what it means is permutes the leaves. So you see C star to the N permutes these leaves because the action is given by diagonal matrices, and these diagonal matrices commute with exponential that defines the leaves. And therefore, you can think of this picture. You have Cn, an open set foliated by a locally free action of Cm, and Cm acts permuting the leaves. And this permutation therefore sends one point in the transversal to another point of it. So M has an action of a very, very large so this is what I tell you, this is the lemma. So therefore we have a complex manifold, and Bogomolov, you can say, well, you have a very small number of manifolds, but Bogomolov has conjectured that every compact complex manifold W can be obtained by this process. Namely, there's a singular holomorphic foliation in projective space, and your manifold, you can put it there, embed it there, transversality outside of the singularities, and that's the way you get a complex number. There's reasons to believe that is true, even though it looks very... So now let me give you some examples. So suppose that the convex hull is a simplex, and in this case, none of the facets contain zero, and you can prove that in this case, what you obtain, the manifold, is a complex torus. Every complex torus, including Jacobian varieties, abelian varieties, every complex torus is obtained by our construction. And in fact, when n is 3, so you have one differential equation acting in C3, satisfying the Siegel condition. Then the set of Siegel leaves, the union of the Siegel leaves, is the complement of hyperplane, coordinate hyperplanes. And you can see that you get a one-dimensional an elliptic curve, and every elliptic curve is obtained this way. The second example, suppose now you have a triangle, but one of the vertices has multiplicity 2, or then you get or a higher multiplicity. So you have two simple vertices, and one vertex of the triangle has some weight m, and then you get all Hopf surfaces or linear Hopf surfaces. So you obtain all Hopf surfaces, you obtain all tori, and then you have products of spheres of all dimensional spheres, which are all Calabi. So all Calabi-Ekman manifolds are obtained this way. So by this simple construction of having a manifold transverse to a linear action, you have, but you have more. In fact, Santiago López de Medrano has shown that for one differential equation, you can have actually things that are connected sums of products of spheres. And Laurent Mexeman and Bosio have obtained that you have torsion in homology, have very complicated homology, and these beautiful, these manifolds have really beautiful topology. very rich and interesting. So in fact, what we wanted to prove is non-symplectic manifolds, and there's only one symplectic and Kähler case. Corresponds to the simplex. So following are equivalent. N is symplectic, N is Kähler, N is a complex torus, or this. This fourth condition means that the convex hull is a simplex, and every vertex is has weight 1. Well, but now we say, well, but what about algebraic? I mean, related to the previous talks of Elisa and Fiammetta, how, or even to the title of the conference, how is this related to toric manifolds, toric geometry, to rationality, irrationality, etc. So what happened is the following: is that you can also prove, we also prove, in fact, it's a theorem by François Lescure and Laurent Merseman, that the manifolds we obtain are actually equivariant compactifications of abelian groups. Usually very complicated abelian groups are called Cousin, groups de Cousin. Of course, the universal covering is Cn, the additive group Cn, but divided by some complicated discrete subgroups, not necessarily lattice like the ones. And so that means that these manifolds are actually, in some sense, a natural generalization of toric varieties, because, I mean, it's not C star to the N that acts with a principal orbit, but actually a very complicated abelian complex group, connected group, with a dense orbit, and it's a compactification of that. And so already begins to smell like perhaps it's connected some way to algebraic geometry, to toric manifolds. And that's the way we arrive in a paper by Laurent Merseman and myself, that there's a very good connection between our manifolds and toric manifolds we call generalized Calabi-Ekman. So suppose the configuration is admissible, so satisfies the Siegel and weak hyperbolicity condition, and suppose that this system of equations satisfies the following property K. The configuration satisfies K if the dimension over Q of the vector space of rational solutions of the system above is maximal. In other words, it's of dimension n minus 2n minus 1. So here is the connection with our conference. This is a rationality condition. Think of this as the analog of quotation marks of rational polytope. And so, of course, you can perturb this a little bit, because something I forgot to say is the following. You have a configuration satisfying our hypothesis. You have a compact complex manifold, which in general is not Kähler. But then what happens if you perturb the polytope? Well, we show with Santiago López de Medrano that actually you perturb the complex structure. And in fact, every deformation, versal deformations a la Quaternionic is obtained that way. So, in fact, two configurations give rise to the same complex manifold, if and only if they are complex affinely equivalent. You can go from one configuration to the other by a complex linear transformation followed by a translation. So you can actually study the deformation space, etc. And so this is the rationality condition. And what happens with this is the following theorem: is that so let n be one of our manifolds correspond to a configuration which satisfies the rationality condition K. Then n is a cipher vibration in complex tori, compact complex tori, of dimension m over a quasi-regular projective toric variety of dimension n minus 2n minus 1. So so that means our manifold was not have anything to do with algebraic geometry, but it satisfies some rationality condition. It's actually a generalization of Calabi-Ekman. It's something that fibers holomorphically over a toric variety, and the fiber is a torus. In fact, it's a cipher. I mean, the dimension. I mean, all the tori are isogenous, you know, and so this is a nice connection. As a particular case, so we obtain all the Calabi-Yau, you generalize completely the examples of Calabi and Ekman. And because the K condition is a countable set of configuration, but it's a dense set of configuration. That you have a configuration, you can tilt it a little bit, arbitrarily small deformation of the convex polytope to satisfy the condition, rationality condition, and therefore you have this corollary. Every manifold n corresponding to an admissible configuration is a small deformation of generalized. I see the time is going very fast. Well, you say, how do you prove that? Well, this theorem from the fact that n admits a holomorphic locally free action of Cm, and the n-dimensional foliation given by the leaves, this we call the canonical foliation, has the beautiful property that is transversely Kähler. So our manifolds are non-symplectic, non-Kähler. They happen to be just compact complex manifolds, but they are equipped with a beautiful locally free action of Cm. And that's when we thought, I remember thinking with Laurent Mercer, maybe you can tilt a little bit the foliation so you make them compact. And that's the condition, the rationality condition arrives. And therefore, if the leaves are all compact, well, you have our foliation. So that's, and the existence of that free action and locally Kähler is because, as I told you, the manifolds are equivalent compactification of a group, of an abelian group. And there you can choose some spaces in a very clever way so that you obtain this free action. So everything is equipped. And well, that's so now we have a connection between a family of complex manifolds obtained in using dynamical systems, and with a rationality condition, you go back to algebraic geometry, which proves that every theorem is reducible to dynamical systems. I remember I made that joke, but somebody told me, yeah, but remember that toric manifolds are actually given by dynamical system, like given by a C star to the n action with a principal orbit. Okay, but I thought I mentioned that dynamical system is very universal. Not only algebraic geometry is universal, but also dynamical system. And actually the reciprocal is true. Any toric variety with simple singularities admits a Cypher vibration by tori, so that the resultant manifold is one of ours. So therefore, in a sense, this is the whole, give you the whole picture of every toric variety like that. And this is the thing. And actually, you can associate a polytope like the two previous lectures by Elisa and Fiammetta. You see, you have M1 is this transversal that I described. It is the intersection of this transversal with the sphere. It's given by these equations in Cn. You know, it's just an intersection of quadrics. And you observe, as I mentioned already, that if you multiply the coordinates by here you need you multiply each coordinate by a unit complex number, it remains simple. So you have a natural action of the circle, sorry, for the n-dimensional torus here, given by this n-tuple of unit complex numbers. And therefore you can take the associated, here is the relation with a moment map and the convex hole. So you have a naturally associated this convex space, given explicitly like that. And so you can associate to every manifold, LVM manifold, a convex polytope, and actually a theorem a little bit a la Delzon. You can go from one of our manifolds to a convex polytope, from a convex polytope to one of our manifolds via a sort of the Zan construction. Well, so this is and now we arrived to two different convex polytopes. One is the original configuration, satisfying the serial condition, and the other is this polytope. So the two polytopes are related by something called the Del Sant. It's called the Del Sant. The Del Sant. Sorry, the Gale transform. The Gale transform. Sorry, you go from one to the other by the Gale transform. Okay. Okay, si continua. Okay, now, well, I want to go to, can I do that for the Quaternionic case? And here is because I see two of the participants are Italian, Elisa Fiammetta, and so this is so this is work in progress with Daniele Zudas. So the notion of toric manifold, quaternionic toric manifold, was introduced by Graziano Gentile, Anna Gori, and Giulia Salfati. So if M admits a symplectic form, well, we'll see. Here, okay. So if you have a symplectic form, then you take the square of the form, and it's what is called fourplectic. So it's not a two form, but a form. It's naturally the quaternionic set. And so you have this definition. A fourplectic form on a smooth four-dimensional manifold is a closed differential fourth form omega such that the wedge product is nowhere set. So it's exactly a symplectic, except instead of dimension 2, you have dimension 4. And then this Italian school have given a definition. So let them be a connected compact four-dimensional fourplectic manifold where this SP1M, here SP1 is simply the group of unit quaternions. So it's the sphere S3 isomorphic to SU2. And you see, we want to generalize the notion of toric manifold. The natural thing is, instead of taking an action of C star to the N with a principal orbit, with a principal dense orbit, well, you take an action of H star, where H is the skew field of quaternions, and you take away 0, and then is something of dimension 4. Then you take the product of those, and so you want something that is acts effectively in a generalized Hamiltonian fashion with split principal orbit. So it's a natural generalization of toric manifold in the setting of quaternions. Now our quadratic equations are perfectly suited for this quaternionic setting. So again, you have to M and N two positive integers satisfying this condition, N greater than 4 and this condition. And you have an N tuple of vectors, but this time the entries are not complex numbers, are H. Blackboard H is the skew field of quaternions. So you take this vector of quaternions. You again take the convex hull in HM, and you have exactly the same conditions, admissible configuration, weak hyperbolicity, etc., etc. So I'm going to mimic everything we did for the complex case. Now consider the intersection of, well, remember I told you that capital T is reserved to the complex, small t to the real, and Blackboard Q to the quaternions. So you consider this family of equations. It's exactly the same thing, except now it's quaternionic. And then you do the same thing, you take the solutions, you do exactly the same thing, no? So this, you see, is very interesting because this equation, you see, in the case of the quaternions, you have the left-handed quaternionic projective space and the right-handed quaternionic projective space. Namely, if you take a Q1, Qn in H to the n, a vector of quaternion entries, then the line, you have the notion of line, you have the left line, and you have the right line. You multiply on the left by lambda, or you multiply on the right by lambda, and therefore this equation here can be projectivized in the quaternionic sense. And therefore, if the condition is I get a manifold, wait, making a mess. So that's we obtain exactly the same way we have a quaternion. Now here, quaternionic is there's a whole school by Graziano Gentile, Struppa, the Scuola Fiorentina of quaternionic, a regular quaternionic manifold. So this manifold is fantastic because you have a machine, you have quaternionic manifolds. The same way as I started saying that Professor Sottile was actually interested in real toric manifolds. So this goes into reals, it goes into the complex, into the quaternionic. Of course, the octonians, I forget it. I'm already dyslexic, so with non-commuting, I have problems. Non-associativity, I don't even dare to enter. And so you have these things. And but now something more interesting happens. Remember that in the previous case, you have an action of we used to multiply by unit complex numbers. There's a C1, C2, Cn. But now you can multiply on the left, on the right, and you have an action of products of spheres. You see here you have most general action. So it's toric, left toric, right toric, and you have a left action. So S3 acts on these manifolds, S3 to the n acts, and it's really, really very interesting. Except now, in some sense, you have lost the irrationality because the sphere has it is not something like so anyhow. So we have, suppose you have a configuration that satisfies our condition, then you have this manifold, this smooth manifold of real dimension. This acts on this unity sphere, SU2 acts on the left, acts on the right also. And well, now you see you have, for instance, the analog of Daniele Angela and Cynthia Bizzi. Many Italians work in this. Actually have a theory of quaternionic Hopf manifolds. Well, in this construction, we can get their examples. And also, they are working on, this work in progress, they are doing the notion of quaternionic Calabi-Ekman manifolds. But you see, in this case, the torus is the unity sphere, S3 n times. And so this is work in progress with a very rich structure. But since I come from the dynamical systems, how is this related to dynamical system? Well, let me go to this. You can actually, you see now you have a linear equation in the quaternionic set. The quaternionic exponential is horrible. It's beautiful, but it's a really complicated object. The non-commutation makes it very difficult. But here you see, remember our original vector fields, you have these vector fields. So in general, you cannot integrate them, but Daniele Tsudas found a condition for, you see, compute it. So the integrability condition is the following, is that if you have this condition, if there's a matrix source that satisfies this, then the system is, so you can actually foliate quaternionic space Hn with leaves having a transverse structure, which is a quaternionic manifold, when you have all the notion of the by the Italian school of the regular quaternionic manifolds, etc. And with that, I finish. So this is work in progress. So I will tell you if we were succeeding in finding a quaternionic analog of PUC. Thank you very much.
We can always put these little hands up and whatnot. Thank you, Alberto. It's extremely interesting. This generalization.
As usual, I make a mess. I think other things that I had, but anyhow, I try my best.
No. It's very nice and very clear. Is there any questions from the audience? Well, let me just ask a question.
Okay.
So just to make kind of an just to leave the setting. So now, if you have a polytope that is the dual of the triangulation of a sphere, one of these polytopes, then whether rational or not, you can associate to it one of these complex, not symplectic manifolds. That's right. But this complex, not symplectic manifold is not the information of the polytope also gives to you this foliation on this holomorphic foliation. This complex manifold.
Gives you the whole package.
And now my question is, and that's the complex case. This is the LBM theory. My question is, in the quaternion realm, how far we are along this picture? How far? What have we gotten so far? What have you gotten so far?
I'm at the very, very beginning. That's what the title of my talk in the after say the first steps. So I'm just learning how to walk. I'm starting to learn the theory from Graziano Gentile, Strupa, what it means slice regular, because now you have an S2 worth of complex structure, and it's a very I'm just exploring. So this is the very beginning. I cannot answer because I'm just, it's like a little kid just learning how to walk. And
but you do expect to get an LBM theory.
I expect to get.
And what would be the expected? What would be the polytopes that appear there? They are more or less special.
They're special because you have dimension 4 to the n. And let me give you an example. Okay, good question. So I say every elliptic curve appears this way. Remember, in the complex case, you have one differential equation in C3, and you give, our manifold give you an elliptic curve. Okay. Now in this case, you have to take h to the 5th. Because so in H4 in the skew field of quaternions, take the simplex, so it has 5 vertices, and suppose 0 is in the origin. Okay, this is your configuration. See, already there's an obstruction because you have 4, right? And the resulting manifold is 3 crosses 3 crosses 3. 4 times. And if you projectivize, that is 3 times S3 times S3. So before you have S2, 1 S2, namely the torus with the complex structures, so that's called an elliptic curve. Now you have S3 crosses 3 crosses 3 with a quaternionic structure. So it's a toric variety, it's a torus actually, no? So a quaternionic torus, by definition, is the unit quaternions to the power n. And you see you have a restriction because the coordinates are multiples of 4, but that's the only obstruction I see.
But it's also highly non-abelian.
Highly non-abelian, and you see you have left action. Before you used to multiply the coordinates by a unit complex number. Now you can multiply on the left by a unit complex quaternion, and on the right by unit. So you have in one sense, more beautiful. But now you don't have things like like a complex, you see in the previous case, like in the work of Elisa and Fiammetta, you had dense suburbs of tori or things like that, no? Corresponding to irrational lattice. Now you don't have that because S3 is compact. But I don't understand. And also, you see, S3 contains the unit circle as subgroup. And so you have toric varieties contained naturally in this thing. But I'm just beginning. I haven't understand. I don't understand the whole picture.
Yeah. But yeah, in that example.
But you think it's a very natural, no? You start by the simplex in the unit in the.
What it's very different here. What it's very different here is that, as you say, the universal covering of the circle is the line.
Exactly.
That is compact, is non-compact.
Exactly.
While the universal covering of this
S3 simply connected, so you don't have that.
It's S3 already.
That's right. But you have beautiful examples, products of the spheres. For instance, you get quaternionic, in this construction, you get a quaternionic projective space. And the analog of Calabi-Ekman is a quaternionic manifold that fibers over a quaternionic projective space. And here you see it is solved that there's left quaternionic space and right quaternionic space, because there are left lines and right lines, right? Forget about it. So you have a left quaternionic space, and the fiber is a torus for its S3 cross S3. So you have the analog of.
But I think that thanks to your example, I see how the non-commutative geometry looks, because one has to do 2 steps higher in the homotopy theory. So it's going to, we can talk a little bit more about it. I can tell you.
Because I don't see so much. The only thing that is wrong with this talking about that in this talk is I don't see any irrationality for the moment. Well, I don't see how irrationality.
There is. I claim that there is, and we can talk about it.
I think okay, very good. Sorry that I was a little bit confusing. I hope I was at least able to transmit a little bit of what the work is about.
No, very nice. Thank you so much.